All right, Titans, we're back for some more Vertex form today. But first, I was doing some yard work the other day, and I was using a shovel to dig so I could put some plants in. And as I was using the shovel, I was thinking, man, the shovel, that invention was groundbreaking. Okay, you didn't like that one? Well, I have a joke about construction. Actually, no, I'm still working on that one. But how about I tell you the one about the nachos I had the other day? Actually, that one's a little too cheesy for you. I'm going to move on. Okay. All right, so vertex form, we know it's f of x equals a, and then x minus h squared plus k. The a is the same as all the other a values that we've been talking about with quadratics. So in this example, our a value is -1. And we know that the a value always tells us if the graph opens up or down. Because it is negative, the graph will open down. And anytime a graph opens down, graph of a parabola, that is, opens down, we will have a maximum. So we know quite a bit just from the a value. But more importantly, vertex form gives us the vertex. And as we learned yesterday, the vertex is always the opposite of what's here, and then the y value is your k. So our vertex, from vertex form, it's the opposite of what's here, so the opposite of +5, so -5, and then whatever the k value is, which in this case our k value is +3. So vertex form gives us direction of opening, but more importantly it gives us the vertex. Today we're going to start comparing graphs, and we're going to see how vertex form actually tells us quite a bit about the transformations of the graph. Whether it's translated, reflected, dilated. And this will actually hold true for all the different function families. So it's something that when we get into graphing absolute value equations in 2 weeks, graphing is going to be super easy because it's basically everything we're about to learn right now, just with a different function family. So first off, f of x equals x squared. That is the most basic quadratic equation. And we refer to it as a parent function. So every function family has a parent function, and it's kind of like the function that other functions in that family come from, like a parent, right? So it's our parent function. And if I look at the parent function on this graph, it has a vertex, as we might expect, at 0, 0, right? There's nothing added in the parentheses, there's no number at the end. So it's not shifting any direction, it's just going to have a vertex of 0, 0. But when we take an equation in vertex form and we put some numbers in, that's going to change our vertex. So the vertex of this one, opposite of -3, and then whatever number's here, which is 1. So our vertex is at 3, 1. Now if you notice, the two parabolas are the same exact shape still, right? They're not any wider or skinnier. They're both still facing up, so nothing changed with that. But what changed is the entire graph moved 1, 2, 3 to the right. And then it shifted up 1. So we can look at the vertex form and we can say, hey, if the vertex went to +3, right, because that's -3, the vertex is now at +3. Well, how does that relate to a +0? Or not positive, to 0. +3 is 3 bigger than 0, or 3 to the right. So the whole graph moved 3 to the right. We also know that our k value is 1, which means our vertex has a y-coordinate of 1, which is 1 higher, or 1 up, from the original vertex. So this graph got translated, it shifted, right? It shifted 3 units to the right and 1 unit up. You might be able to make a prediction on this one just by looking at it, what's going to happen. But let's go back to our parent function. So that's my red one. It has a vertex of 0, 0. Right here, 0, 0. And then our new function has a vertex. We can look at the graph or we can look at the vertex form. But opposite of 2, so -2, and then -4. And I can double check, -2, -4. And so compared to the parent function, where did this graph shift? Well, because my vertex is -2, that's 2 left of 0. So 2 to the left. And then the y-coordinate is -4, which is down 4 from 0. So 2 to the left, down 4. 2 left, down 4. So we can look at the vertex and know that, hey, if the x of the vertex is -2, that means our whole graph shifted left 2. And if our y-coordinate is -4, we know the whole graph shifted down 4. And this is going to hold true for any function family if we put it in this vertex form is really a type of transformational form. And every other function family we can put in this form to move it left and right, up and down. But what about the a value? So now I'm not going to worry about changing the vertex. I'm not going to shift it left or right, up or down. All I'm going to do is change the a. So our parent function, right there, that's the red one. All three of these have the same vertex because we're not shifting it, right? We're not changing the vertex. But what do we notice about these three graphs? Well, the red one was our parent function. That's like the one we start from. But the green one is skinnier, and the blue one is wider. So if we look at the green one was skinnier. Well, how is this equation different from the original? Well, our a value got bigger. This a value is 1. This a value is larger than 1. So a, let me use the right color here. A is larger than 1. Because the a value is larger than 1, what happened to the graph compared to the original? Well, it got skinnier. So it got skinnier. That was interesting. But what we call that mathematically when it gets skinnier is it's getting stretched. It's kind of like you take your arms and you stretch them, right? Instead of here, they get stretched, and so they become narrower or skinnier. So that's called a stretch. And this one, because it's 4, it would be stretched by a factor of 4 or dilated by a factor of 4. If you look at the blue one, the blue has an a value that is less than 1. Not negative, right? Just it's between 0 and 1. So a is between 0 and 1. It's not 1, right? It's smaller than 1. It's not 0, it's bigger than 0. It's somewhere in between. So if your a is in between 0 and 1, your graph gets wider. Mathematically, we have a special name for when it gets wider. We call that a compression. Kind of like you got your arms, somebody pushes down, and it compresses, and it makes your arms go wider, right? So they're getting compressed. So again, skinnier is a stretch, wider is a compression. If your a value is between 0 and 1, then it's going to be a compression. But if your a value is larger than 1, it is going to be a stretch. Now we'll talk about on the next slide what happens if we put a negative in front. When we're talking about between 0 and 1, we also mean between 0 and -1. So if your number is between 0 and -1, it will still be a compression. And then when we say larger than 1, we also mean if it's a bigger number than 1, even if it's a negative. So if you take 4, but make it negative, like -4, that would also be a stretch. Okay, the other thing we can do with the a, other than changing its value, is we can change the sign. So this one has a positive a. We know that opens up. But what happens if our a is negative? It opens down. So when we change our a to a negative, that is a vertical reflection. So vertical meaning up and down, reflection meaning mirror image. If we go from a positive to a negative, it's going to reflect vertically. It's going to flip upside down. All right, so in summary, don't get too excited, we're not quite done yet. But in summary, if the number in parentheses is positive, so if we have x plus 3 squared, if this number is a positive, what happens to our graph? Well, the graph will shift positive, opposite, negative. It's going to shift left. So this particular graph would shift left 3 because the vertex would now have as its x-coordinate, your vertex would be -3, comma, something, right? So if my vertex is -3, the whole graph is shifting left 3. If the number in parentheses is a negative number, such as x minus 5, then we know that our vertex will be the opposite of -5. So the x-coordinate will be +5, y-coordinate will be something else. But if our vertex has a +5 in the x, that means the whole graph shifted right. So this particular graph, if it says x minus 5, that means our vertex is at +5, which means it shifted right 5 units. And these are all translations because we're just moving the graph, we're not flipping it or making it skinnier or anything like that. As far as our k value, if we make our k positive, so let's say we have x something squared and we have +2. That +2 is going to move the whole graph up. So this would be a shift up. Shifts up. This particular one would go up 2. If our k value is negative, so we have something in our parentheses, right, and then we have -5, we know that this will move our graph down, so it's going to shift down. And this particular one, because it's -5, it's going to go down 5. So a little bit of a recap of what numbers in those different places will do. And then as far as our a values, if a is negative, it will be a vertical reflection. It will flip it upside down. If a is between 0 and 1, or 0 and -1, then it's going to make our graph become wider. So it's going to be wider, which is what we call a compression. So an example, let's do 0.5x squared. This is dilated or compressed by a factor of 0.5. If our a is bigger than 1 though, or, because you have to go opposite, if it's smaller than -1, so something between -∞ and -1, then it's going to stretch. Whoop. So this is going to be skinnier, which is going to be a stretch. An example of a stretch, let's say it was -5x squared. The negative will reflect it, but then the 5, because that's bigger than 1, or -5 is smaller than -1, that is going to stretch the graph and make it much skinnier. All right, hopefully you can read those. It's a little small, but want to go through 5 examples and just quickly point out the different transformations that we know from vertex form. So first off, if a is positive, will the graph open up or down? Up. Let's go through this one. A is positive. Up. A is also positive. But then these next two, our a values are negative. If the a is negative, the direction of opening will be down. Okay, our vertical dilation or stretch or compress, so we're looking at the a value and whether or not the graph's getting skinnier or wider. If our a value is 1, it's not going to be any skinnier or wider than the parent function because it's the same a value. So I'm going to put nothing, right? It's not any different. But if our a value is 4, which is a number larger than 1, that is going to make our graph skinnier, which is what we call a stretch. So the vertical dilation is a stretch with a scale factor of 4. This one is 2/3, and 2/3 is smaller than 1, right? So it's between 0 and 1. We know that if it's bigger than 1, it's a stretch, but if it's less than 1, between 0 and 1, that is going to make the graph wider, which is what we call a compression. This one is -1. So again, it's the same as the parent function. It's a 1, right? It's just negative, so it's going to be upside down. But because there's no number other than -1, it's not going to be a stretch or a compression. But we can make a side note that it will be reflected, right? Because it's going to be reflected up and down. And then the last one is -4. So again, like this one, it will be reflected. But we have a -4, right? And since 4 is bigger than 1, that's going to be the same as this one. So it's going to make it skinnier, or we're going to call that a stretch. The only difference between this stretch and that stretch is this one is opening up, and this one's going to open down. But it's still going to be skinnier than the parent function. Horizontal translation. So horizontal translation, we're looking left and right. If this is -2, that means our vertex will be at +2. And if our vertex is at +2, that means we went right 2. This one, there's no number with the x, there's no parentheses. So that means your vertex is going to be at 0 something, which, well, it'll be 0, 1, right? But as far as horizontal, left and right, it does not shift. So no shift. This one has a +4, which means the vertex will be at -4 something. And if our vertex is at -4, that means our graph went to the left. So this went left 4. What does the -6 mean? Well, our vertex will be +6 something. And if our x is +6, our graph went to the right. So that is right 6. And then finally, this last one, we have +7, which means your vertex will be at -7 something, which means -7 is to the left. So that is left 7. And then finally, if we look at the vertical translation, that means how much we're moving up and down. And translation does not mean reflected at all. That's totally different. So the translation is how much we moved up or down. And that's always just your K value, right? It's not your C value because we're not in standard form. It's our K value because we are in vertex form. If my K value is 8, that means my vertex has a Y coordinate of 8, which means we moved up 8. This one has a K value of 1, which means our Y coordinate is 1, so that is up 1. This one we have -9. I think you're probably getting the hang of it. That means we're going down 9. Our K value is +3, so that is up 3. And then this one, there's no number added or subtracted at the end, so there's no K value, which means our vertex, although it did shift 7 to the left, the Y coordinate will be 0, which means there was no vertical translation or no vertical shift. All right, hopefully you're getting the hang of it. We've got one slide left, and this is basically the opposite of what we just did. It's taking some information and writing the equation in vertex form. So we're going to start with our parent function, x squared, and we're going to perform specific transformations to it. So I want to go 2 units up and 7 units left. Well, it didn't say anything about stretching or compressing or reflecting, so I'm not going to change my A value. But if I wanted to go up 2, that means at the end I have to have a +2, because the K value is what shifts up and down. If I want to go 7 to the left, I know that my vertex, so essentially if I go to this, if my vertex is 7 to the left, that's -7. And if it's up 2, that's 2. So if I want my vertex to be -7, what has to go in here? What will actually shift it 7 to the left? Well, it's the opposite. We have to put plus. So to go left 7, we do the opposite, which is +7. Our next one, we need to have a stretch with a dilation factor of 6. We want to translate up 1 and 4 units to the right. So we've got a lot going on this one. If I want to stretch it with a dilation factor of 6, what does my A value need to be? Well, a stretch we know needs to be bigger than 1. And it says it's stretched by a dilation factor of 6. All that means is your A value is 6. Inside the parentheses, this is going to be our left and right. Well, I know I want to go 4 to the right, which would give me a vertex of 4. And then 1 up would be a 1 right there. So if I want to go 4 to the right and get a +4, I need to have the opposite inside the parentheses. And then if I want to make it go 1 up, that's +1. A vertical reflection, 1 unit down, 2 units left. What will this equation look like? Well, to reflect it, we need to make our A negative. It didn't say anything about a stretch or a compression, so I'm not going to change the number of the A. It's still going to be 1, so it's just a -1. If I want to go 2 to the left, that means I want to go that way, which means my vertex is -2, which means in my parentheses I have to have the opposite. So x +2 squared. And then 1 unit down is just -1. 2 more. A vertical compression. So if it's compressing, we know it's going to be a number less than 1. And in fact, it tells me that it's going to be a factor of 1/2. So it's going to be +1/2, or 0.5 would be fine. And then we're also going 3 units to the right. If we want to go right and left, is that at the end or is that in the parentheses? Well, if we want to go right and left, that's horizontal. That'll be in the parentheses. And we know it's going to be the opposite. So if I want to go 3 units right, which would be a +3, my vertex form is going to have the opposite. So x -3. And then we still need to always make sure we put the squared to make it vertex form. Do I need a number here? Nope, because it didn't say anything about shifting up or down. All right, last example. A vertical reflection. A vertical stretch with the dilation factor of 3, and translated 2 units down. Okay, so we've got 3 things we need to do. First thing, how do we make it reflect? Well, we make our A negative. If we wanted to have a stretch with a factor of 3, we put -3. And if we want to have it go 2 units down, that means at the very end we need -2. But there was nothing about left and right. So I don't need to put the parentheses. I can just put x squared. So -3x squared -2. All right. Hopefully you're doing okay with vertex form. We've now covered all 3 main forms of a quadratic. We've done factored form, standard form, vertex form. Each form gives us something different. It tells us information that's helpful, and it's pretty rad. All right, guys, hope you're doing great. Go Titans, go math, keep doing your work. We're almost to the finish line. You got this.